Okay, everyone, good afternoon. So your bonus quizzes are due tomorrow. So, we decided that sulfuric acid is probably going to be better because we already have hydronium ion in solution ready to attack carbonate ion. We also have HSO4 minus. So we basically have a double acid attack going on here with just one thing. So, yesterday we started to evaluate K. We realized we had to multiply through by a variety of factors. I asked you guys to go ahead and combine these. You should have gotten this answer. Ka, hydrogen sulfate ion, times Ksp, calcium carbonate numerator. Ka, H2CO3, times Ka, bicarb, times Ksp, calcium sulfate denominator. Hopefully you were able to get that. Once again, all you have to do is take a look at this. Do your Kas, Kbs first, and then you'll be just left with Ksps. You can figure out where those go. So, does anyone have any questions on what we did for H2SO4, sulfuric acid? Okay, good. So, moving on from there, we'll take a look at what happens when we treat this system with hydrogen sulfate ion to make calcium sulfate. And in this case, in order for the stoichiometry to work, we have to pay close attention to that. We're going to be left with bicarb, not H2CO3. So we can evaluate this K. My first step, write what I've got in my equation. Recognize the chemistry here. Once again, no pure solids, no pure liquids allowed. Now I have to go through, again, multiply through by various factors of 1 to get me to where I need to go. Now the first thing that I'm going to do, I realize I've got two semi-soluble calcium salts. I need calcium ion if I'm never going to be able to solve this problem. Introduce calcium ion. Now I also take a look and I say, well, I have calcium carbonate, not calcium bicarb, and I've got calcium sulfate, not calcium hydrogen sulfate. So I'm going to need to generate those two species before I can ever actually make them. So I'll include a factor of both of those as well. I'm going to realize, while I'm looking at this, I see, okay, I see hydrogen sulfate ion has to act as an acid, give its proton to carbonate ion to generate the sulfate ion that gets scoured by the calcium ion, and the bicarb ion, which is a product. So, I realize this thing has to act as an acid. I'm going to need to use Ka. One thing I'm going to be missing from the Ka expression, concentration of hydronium ion. Now, this looks pretty good. Let's start writing things down. So for starters, I'll pull out Ka HSO4 minus. HSO4 minus, conjugate base, hydronium ion. I've got that now. I'll also write down Ka for bicarb, because I know if I start over here and read this from right to left, bicarb acts as an acid, gives its proton to sulfate, and is scoured by calcium 2+. So, I'm going to look for inverse Ka, HCO3. So I see that, bicarb ion, conjugate base, hydronium ion. So I'll write that in my denominator. Okay, next step. I know I've got two semi-soluble salts. The answer's sort of going to fall out on us here. Calcium carbonate, KSP, numerator. Calcium sulfate. KSP. Denominator. Now, what I'll ask you guys right now to go ahead and do, I don't have my calculator with me. I'll ask you guys to go calculate the volumes of these. You should have all this information on your information sheets, KAs, KBs, relevant KSPs as well. So we can now prove to ourselves that the one on the left-hand side is going to be larger. So once you have a number for either one, just go ahead and yell it out. Yep.
The first one's 4.1 times 10 to the 11.
4.1 times
10 to the 11.
10 to the 11. Sounds about right. The cheap way to get to the answer on the right is just going to be to go ahead and multiply by KaH2CO3. Yep.
1.7 times 10 to the
1.7 times 10 to the 5th. That's a little bit like a question, but it's probably about right. So, we recognize, not only is this bigger, but it's about 1,000,000 times bigger. So I realize my double acid attack from H2SO4 is a much more effective dissolver of calcium carbonate than the singly acidic hydrogen sulfate anion. So any questions? That's a little bit more practice, evaluating a complex K. Hopefully at the end of class today I'll have a couple examples where we look at complex Ks, and I think those are just about as hard as it gets. So these are pretty easy examples. If you have any questions there, stop me now and we'll talk about them. If not, we'll carry on and look at some harder ones a little bit. Okay? So moving straight forward, we're going to talk about section 19.4. Dissolving a semi-soluble salt by complex ion formation, which is nothing more than a special extension of little part E, as Horvath mentions in the book. Now, you guys have worked with some complex ions in the past. Can you name one of them?
AlOH2 6.
these are our non-molecular polyprotic acids. And these are really the simplest examples of complex ions. Now, what is a complex ion? Dr. Horvath's definition. Complex ion is an ion composed of a metal ion, aluminum, iron. I think you guys have magnesium on your tables as well. Composed of a metal ion, bound by coordinate covalent bonds. Just covalent bonds, we include coordinate in there, just to specify. To surrounding groups called ligands. In this case, these water molecules are known as ligands because they are bound directly to metals. Therefore, note that species such as iron with 6 waters attached to it, aluminum with 6 waters attached to it, these are complex ions. Now, these are also known as Lewis acid, Lewis base adducts. Lewis acid, Lewis base. You guys are going to have to know what those are. A Lewis acid. The species that has one or more empty orbitals capable of accepting an electron pair from an incoming atom or molecule. I'll show you guys in just a minute that it's one of the non-bonding pairs in water on the oxygen atom that bonds directly to the aluminum. The aluminum contributes no electrons. So, Lewis acid, acceptor. That's the way I always remembered this stuff when I was learning it. Acid, acceptor, A. It's easy. Lewis base. Electron pair donor. In this case, this is going to be water. You guys will look at later on in the semester. One of the last units you do is on elementary inorganic chemistry. Dr. Horvath loves inorganic chemistry. I believe that's the specific study in which he got his PhD. I also study inorganic chemistry. It's wonderful. You will like it. No. Anyway, so, Lewis acid, electron pair acceptor, in this case, aluminum, iron. They have empty d orbitals, they have empty p orbitals. These are capable of accepting electrons. Lewis bases. Any species with a lone pair of electrons can be a Lewis base. Water's a good example.
But aren't Bronsted-Lowry acid and bases technically donating and accepting electron pairs as well?
When we deal with Bronsted-Lowry chemistry, we think about protons.
Yeah.
If you want to think about electron pairs, I suppose you can, but the best way to think about it is Bronsted-Lowry talks about proton transfer.
Yeah.
And in this case, we're just talking about electron pair donation acceptance. So there are no protons.
Can I think about a Bronsted-Lowry acid in terms of like electron movement?
Well, using the different definitions, they each have their own advantages, so...
Yeah, I guess that's my question.
I would think of the two as different.
Okay.
I would say try not to think about the electron donation when it comes to a Bronsted-Lowry acid, because really you're just losing H plus and picking up H plus,
Okay.
which has no electrons. So technically, H plus is going to be an electron pair acceptor. It's going to be an electrophile, and it's going to find.
I guess that's my question.
So yes and no, because there are some examples of Bronsted-Lowry acid-based chemistry wherein this isn't going to apply. We won't get into any examples of that, but if you go on and study organic chemistry, you'll see that there are some interesting examples of molecular acids and bases wherein these rules don't apply. So we're going to keep the two as separate for now. But as you go on into the study, you'll see that there are important similarities that you'll come to recognize. But for now, they're two completely different. So, Lewis acid, Lewis base atoms. question we have to ask. What do these things look like? We kind of talked about it. I don't know if we've drawn them yet. And it'll be good to see this before you guys go on and do more advanced structure theory in later chapters this semester, or this summer section. So I know I've got my aluminum. Aluminum in this case is going to be a central atom. Let's deal with hexyl aqua aluminum 3. Now, the way that I've drawn this is to draw sort of the shape of this structure. This is an octahedron. I don't know if you guys have studied hybridization and how that results in different structures. You guys should review that. This is sp3d2 hybridized. That's an octahedron. Dr. Horvath likes to draw it as such. You'll see this in the book. He does this canted square thing. Now this is a problem, because what I'm trying to do, what Dr. Horvath is trying to do, when we draw things like this, we're trying to draw 3 dimensions on a 2-dimensional thing. It's difficult to get the correct point across. I'll probably come in one day with some molecular models, show you guys exactly what these things look like in 3D. But I realized that the canted square that Dr. Horvath has drawn at the bottom of 1920 corresponds to these 4 atoms. These 2 oxygens coming out of the board at you, these 2 oxygens going straight behind the board. They correspond to a plane. Now, it's important to note that when Dr. Horvath draws this canted square, this is the way he'll expect you guys to draw it as well. When you guys draw it, these water molecules are not bound to one another. That's the most common problem that's associated with drawing a structure like this. While this does tell you very clearly that all these 4 water molecules lie on the same plane, they're not bound to one another. They're bound to this aluminum. So if I really wanted to be finicky about it, I would draw those bonds in, but then things start to look a little bit more complicated. So Dr. Horvath does not include them there. So just remember, these Lewis-based Lewis acid adducts, when you have what are called monodentate ligands, that means they only bind to the metal in one place, they're never going to be bound to one another. Each of these coordination sites are unique. I prefer this way, Dr. Horvath prefers this way. You'll probably see them both in the future. It's good to know what they are. So this represents an octahedral shape. Let's see here. Any questions on just how to draw these? You guys will get a lot of practice with that in the future. Okay. Have a read at the bottom of page 1920. Dr. Horvath talks about Lewis acid, Lewis-base reactions. Reaction involving the formation of one or more coordinate covalent bonds by the interaction of Lewis acid and Lewis base. He gives you a very simple example, aluminum 3+ plus 6 waters, giving you this. We know that we have those in aqueous solution. You guys have a lot of examples of that on your information sheets. So, how does this apply to us? A couple quick questions regarding the basics. Question 1926. How many bonds could aluminum form just based upon the number of orbitals it has available to it? Theoretically. Now, what's special about that 3rd row in the main group, well, the 2nd row in the main group there? Aluminum, silicon, phosphorus, sulfur. They have expanded octets. Now what does that mean? An expanded octet, that to me says it's still 8, but it's bigger. We need a better definition. Aluminum, silicon, phosphorus, sulfur have the 3 d orbitals available to them. They are empty, but the d orbitals are still present and can be filled. So, bearing this in mind, I see aluminum 3+ has an s orbital available, 1 bond. 3 p orbitals available, grand total 4 bonds. D block, 10 electrons, 5 orbitals, grand total 9 bonds, theoretically. Aluminum can make 9 bonds because it has 9 orbitals available to it, all empty. Now, aluminum 3+ never makes more than 6. So let's just say that, greater than 6. It doesn't happen. Now the question is why? You guys probably haven't been exposed to this terminology before. The answer is called steric hindrance. Picture aluminum 3+. It's pretty big, it's larger than oxygen. We know it's 1 row down, that means it's probably going to be quite a bit bigger. As we go down in the periodic table, we increase in size. So picture aluminum as a soft ball. And picture those oxygen atoms in water as golf balls, tennis balls, something a little bit smaller. Now, if I take a softball, I put 6 tennis balls around it, I can do that. They won't get in each other's way. But if I try to squeeze a 7th one in there, I'm going to start pushing waters closer together, and I'm going to start pushing my other ball close to another one. And they'll repel one another, because oxygen still has unpaired electron density, because it still has one unpaired, or it still has 1 pair of electrons not doing it, not bonding. So, these molecules get in each other's way. This is called steric hindrance. It basically means that any Lewis base, any electron donor, if I have 6 of them, they're going to turn out to be too large to fit a 7th one on. It's called steric hindrance. So, for our purposes, we're never going to see coordination numbers of greater than 6, despite the fact that theoretically, for transition metal and 2nd row main group elements, I could have a coordination number of 9. Coordination number just corresponds to the number of sites I can occupy. 1, 2, 3, 4, 5, 6 for aluminum. Related to that question, 1927. The correct formula for hydrated lithium . Two waters. Same reason. Look at where lithium is. It's even going to be smaller than oxygen. And of course you have your hydrogen factor. Now in this case, we'll take a tennis ball that is lithium ion, and I'll surround it by 2 basketballs. Those are going to be my oxygens. Once again, not exactly to scale. But you understand that point. Now in this case, I can't fit more than 2 oxygens on this lithium. Because, once again, lithium too small. Water molecules too large. Try to squeeze a 3rd one in there. These 2 oxygens are going to start to get in each other's way. I'll only be able to have 2 at a time. So, steric hindrance. It's a term that we give to that. It's a blessing. It's a good thing to know. Moving on from there. Are there any questions on this stuff here? basically just considering the size of aluminum, lithium, the oxygen atom, and water. Okay, so now we're going to get into those final K values that we were taught, or that you guys have seen on your information sheets. KF, formation constants. These are very much related to Lewis acid-base chemistry, because it's Lewis acid-base chemistry that gives us the complex ions to be formed. So, we start off with a specific example, dissolving silver chloride by formation of diamine silver plus. Okay? So this is the reaction in question. This corresponds to the formation of this complex ion. I call it diamine because I give ammonia the name amine when it's connected to a metal center. You guys will learn about this again in a few weeks when you're talking about coordination chemistry in greater detail and inorganic chemistry as a whole. I'll refer to it as that, but I'm just referring to this diamine silver plus ion. So, you see this reaction occurs when silver chloride is dissolved in aqueous ammonia and involves the formation of the complex ion that we've been talking about. Since the water solubility of silver chloride is not affected by changes in pH, it follows that this reaction is not Bronsted-Lowry acid-base. It has to be something else. This is Lewis acid-base chemistry that we're doing now. The reaction does not involve H plus transfer. There's your answer regarding the differentiation between Bronsted-Lowry and Lewis acid-base chemistry. We have to keep the two separate, otherwise we'll get very confused while we're solving problems like these. So, this reaction, a little bit more simply put, will remove the chlorides. Silver plus, floating in solution, plus 2 moles of ammonia, also floating in solution, are going to form that same complex ion. This is the reaction that corresponds to KF, formation of diamine silver plus. Now, as it turns out, I can also quantify this. There's a number involved. 1.7 times 10 to the 7. Now what does that tell you guys regarding the strength of the bonds between silver and the nitrogen and ammonia?
Strong.
Strong, exactly. 1.7 times 10 to the 7. So, not only can we drive reactions, we're analyzing Ks, we can drive reactions by precipitating semi-soluble salts. We can also drive reactions by creating, phase is very important here, aqueous complex ions. That's not a solid, it's again a discharge, just floating around in solution. So, these KFs are very important. We're trying to strategize, we're trying to test for different ions. We can use KF to our advantage, and we're going to do so as we move forward. Now, if I go in the opposite direction, Horvath makes a point. If I want to go from silver, 2 amine ligands on it, to silver plus, my 2 ammonia molecules, this is just going to be 1 over KF. It's going to be the exact opposite. very small number, and we call that Kd, dissociation constant. In this case, they're associating, or forming. If I write it backwards, they're dissociating. That's a good thing to know. You guys, of course, don't have Kd values, the same reason that you don't have Kb values. You can solve it very easily by just taking the inverse of what you need, or going through Kw, or Ronson-Lowry acid. So, those are the very basics. This is just another simple type of equilibrium that we can use to our advantage. Now, let's get some practice with such. So, we go back to our original thought. Dissolving silver chloride by the formation of a complex ion, diamine silver plus. We can calculate this K. So let's do it. Once again, write down phase for all these. So we know what to include and what to leave out. So I see, I've got product complex ion and product chloride. And there's K. Now we can evaluate this using our newfound knowledge regarding formation constants. So, what's going to be a good thing to choose to add into this equation so I can get some things to start to fall out? Silver ion, sure. Turns out that is all that I need. So, I'll take a look. See silver, chloride, chloride silver ion, corresponding to KSP. Silver chloride. And I also see that I've got my complex ion and my two reactants required to make that complex ion. So, that corresponds to, I've written too large. This corresponds to Kf for my silver complex ion. Go ahead and I can do that multiplication. I'm given Kf. We know that. That's a simple physical value. Similarly, KSP. We've got these things. Horvath does the math for us. 2.9 times 10 to the minus 3. Now, it'll follow that silver chloride in the presence of ammonia is much, much more soluble than it is in pure water. Once again, I see this K value, 2.9 times 10 to the minus 3. Compare that to KSP, silver chloride, 1.7 times 10 to the minus 10. Moving up. So, 2.9 times 10 to the minus 3, corresponding to this equilibrium. If we want to talk about it qualitatively, I say, well, it makes silver chloride more soluble by formation of the complex ion you see on the right-hand side. Now, let's talk about the numbers. Question 1928. What forms stronger bonds to silver plus? Ammonia or chloride ion? Answer this by calculating the molar solubility S of silver chloride in 6 molar ammonia. So now we're given some numbers. We're going to be expected to use our K to figure this out. So, Go ahead, we'll once again write the chemistry. Now, I realize that all these species are aqueous except for silver chloride, so I'll ignore that. Now, H3N, how much of it do I start with, concentration?
6 more.
Stoichiometry is important. Start off with 0 this, practically 0 this. Now, how much of each am I going to add? We can call that a variable, call it whatever we want to. Call it S, call it X, call it S. That's an S. Now, how much ammonia do I consume if I make S silver complex and S chloride ion? 2S. Now, math's going to be there for you. Okay, is equal to 2.9 times 10 to the minus 3. And that's going to be S times S, S squared, divided by 6 minus 2S. Now, a lot of people are going to leave that as is. Should you be faced with a question like this on a take-home quiz or on an exam, a lot of people see that, well, gosh, that reminds me of my Bronsted-Lowry acid-base chemistry, so this must be right. No, go back to your K. Remember, this term must be squared. Because 6.0 minus 2S represents the concentration of ammonia. Never lose your chemistry. So, you go through, you start off by rooting both sides, makes it a lot easier. Turns out, for 1 mole silver chloride, I find, if I go through and solve this, I will dissolve 0.29 moles. Dissolve. And I leave behind the other portion of my 1 mole, 0.71 moles silver chloride remain. Now, what does this tell us about the comparative strength of silver chloride versus silver amine bond?
Chloride stronger.
Chloride is stronger by quite a bit. Yep. Now, next question follows. If you answer question 1928 correctly, you proved that chloride ion forms considerably stronger bonds to silver plus than does ammonia. So why is it possible to dissolve silver chloride in H3N solution? Well, I see that I've got a K value here. While it is small, it's less than 1, it's not too far less than 1. This is a similar question to, well, gosh, I see that the Ka for ammonium ion is really, really low, so why does it produce a measurable amount of H3O plus if I put it in solution? Its K is there. It is measurable. It's not one of the really small ones with which we deal, and we can do the math. Additionally, I can take advantage of what we called the gang-up factor before and start off with hugely concentrated ammonia. 6 molar, this is probably some of the strongest stuff you'll deal with, unless you're dealing with pure HCl, which is a little over 10 molar, pure sodium hydroxide saturated, once again about 10 molar. That's about the strongest stuff you'll ever deal with. 6 molar concentration, very, very strong ammonia. So, we drive that reaction to the right as much as possible. And we see that we do dissolve a considerable amount of that silver chloride despite the fact that it yet remains. So, 2 reasons there. Remember your Bronson-Lowry chemistry. Small K's can still result in measurable concentration of products. Additionally, we take advantage of the gang-up factor. Add a bunch of ammonia, we'll see that we start making some silver ammonia complex. So any questions on 28 or 29 before we move on to studying a slightly different system? Okay. Question 1930, for the equilibrium, silver oxide plus water, giving us silver plus 2HO minus. KSP, silver oxide equals 3.5 times 10 to the minus 16. You guys probably have that on your information table. With this, plus any other necessary K data, calculate the S for silver oxide in 6 molar ammonia. We're going to do 4 molar because the answer that Horvath has for you guys there is for 4 molar. You can practice it with 6. It's going to change the numbers a little bit. The chemistry remains the same. So, we've got something new, silver oxide. So does Horvath give it to you here? No. What's my other product? Oxide ion, O2 minus. You guys should cringe when I say that.
Shouldn't it be?
2 hydroxide ions. Remember that. When this thing dissolves, KSP, silver oxide, corresponds to silver oxide in equilibrium with silver plus and 2 equivalents of hydroxide ion. O2 minus does not exist for all intents and purposes in an aqueous solution. 2 moles hydroxide ion. That's important to remember. Now let's take a second look at our stoichiometry here. This is yet unbalanced because I realize I have Ag2O. So I need 2 of my silver complex ions. They're still ions. Which means I'm going to need 4 equivalents of ammonia. Always make sure that your equations are balanced, both by mass and by charge. Charge neutral on the left, 2 equivalents positive charge, 2 equivalents negative charge on the right, charge neutral on the right. Always good to double check yourself whenever you're writing chemistry down. It's easy to miss something. So, this is the chemistry with which we're dealing. Let's talk about K. K for this reaction. Once again, all aqueous except for silver oxide. That's a solid. We'll ignore it. K for this reaction. Hydroxide ion raised to its stoichiometric coefficient times silver ammonia complex ion raised to its stoichiometric coefficient divided by H3N ammonia raised to its stoichiometric coefficient. Now, take a quick look at this. I'm going to see that if I want to compare KSP's and KF values, well, I've got some components of KSP, silver oxide. I've also got a component, KF, for a complex ion. I need silver ion. That's what I'm missing.
I have a question.
Yes?
There's 2 oxygens on the right and 1 on the left.
Inverse reactions.
So, the way that the oxide ion works is it's going to pull 1 proton off of water. So you can balance this using water if you want to. So that's just the way that, you can take that straight from the definition of the KSP for silver oxide, that you need 2 hydroxide ions. So once you dump oxide ion into water, that inventory is just 2 hydroxide.
Okay.
So, yeah. Sorry about that little bit of confusion there.
Would you need to add that to do mass balance expression?
Yes.
Okay.
Yeah, I would include that. So that one mole of water there gets torn apart by the oxide ion. So there's your 2 protons and there's your 2. That's a good point. It's good to be all inclusive. But for the purposes of K, we still ignore that water. It's solvent water and it is pure liquid. So, we move right back to our K. Now we realize that KSP, silver oxide, is going to require me to create 2 equivalents of silver ion. 2 silvers per oxide. If I ever want to get that KSP out correctly, I'm going to have to multiply by silver ion squared. Now, go ahead. Take a look at this. I see KSP, silver oxide. I also see KF for my complex ion. But I see 2 of them here because I realize I've got squared ion, squared silver ion, squared complex ion, and ammonia to the 4th power. So this corresponds to the KF, I wrote it, for my silver complex ion squared. Now you can go through, you can solve for this K. Turns out to be a very simple number if you do the multiplication. I got 0.1. I heard a yeah. That makes me feel more confident. Okay, so let's go ahead, talk chemistry again. In this case, I'm going to start off with 4 molar ammonia. This is going to get a little bit tight. I realize I start with no complex ion, very little hydroxide ion. So, 4 molar ammonia. I'm going to subtract off how many equivalents of ammonia per run of this reaction. 4 times whatever you choose to call your variable. You can call it S because we're dealing with solubility. We're also dealing with formation. Lowercase s is what Dr. Horvath uses for this whole section, so we might as well use it as well. Now, realize I start off with 0 silver ion. How much of it am I going to make per run in this reaction? S. Similarly, hydroxide ion, also 2s. They're stoichiometrically identical. So I can go back to K. K equals s squared divided by 4.0 minus 4s. Once again, don't forget where you're getting this from, K to the 4th power. Yep.
I'm slightly confused. Is it supposed to be 4.0 or 6.0? Minus what?
Dr. Horvath gives you the answer there, that 0.79. That is for 4 molar ammonia. Now you can try it for 6 molar ammonia, you get a different answer, but just so that we're not getting totally confused and backwards, I'm giving you guys all the information for 4 molar.
Okay.
Yeah.
Shouldn't it be 2s squared times 2s squared in the top? Because, okay.
Yeah. Never forget where you're coming from. Absolutely. that should give you, oh, nope, that is not what K is. K is equal to 0.1. And that should give you a value for S that's equal to 0.79 molar. So you go through and solve that. Horvath gave you the answer. You can also solve for 6 molar. Very similar procedure. You start with a different number there in the denominator. Okay. So any questions about this? Basically all we're doing is we're solving for different complex K's using a new value Kf that we just picked up. Okay. So, section 19.5. More on writing equations for reactions. What I'm going to do is allow you guys to read that. If you have any questions about it, feel free to ask any one of us, but Horvath details it all there very well for you guys. So I think it might be a little bit redundant for me to go ahead and go over that. That's study material for you guys. Writing equations is very, very important. What I'll do is we'll go through, stepwise, question 1932. Their questions are asked of you, and we can talk about those. What might be different between some solutions that look pretty similar. So definitely have a read. Bottom of page 1923, well, all of page 1923, top of page 1924. Horvath gives you all the information you need there. No need to go over it again. But question 1932. We're looking at some pretty interesting systems, but we want to talk about the chemistry that occurs. We won't solve any Ks for these, because we've got some good practice going on those later. Okay. Write the correct equations for each of the following. A solution containing cuprate ion is treated with excess 1 molar hydrogen sulfide, dihydrogen sulfide. Now, find the products here. We're given the hint that copper sulfide is much more stable than the complex cuprate ion. So, what's one of our products going to be? He kind of gives you the answer there. Solid copper sulfide. Now, if I want to treat this thing stoichiometrically, what am I going to be left with here? You see that in this case, hydroxide ion is going to be my base. That's not going to be stoichiometric, but that's okay, because we have excess H2S. So, water is going to be my other product here, pure liquid, because the acid-base chemistry that occurs is going to be between H2S and the hydroxide ion that I freed. That's just going to make water. So once again, this reaction that I've written here is not stoichiometric. It would be very difficult to solve for a K for this thing, unless we first went through and balanced it. But these are our two products. That's a pretty simple example. So, any questions on that? No, okay. So calcium hydroxide is treated with 1 molar ammonium bicarb. Find the products. So what do we know about calcium carbonate and its stability in comparison to calcium hydroxide? about this a little bit yesterday. We know that calcium carbonate is much more stable. Write this slightly different way. Separate the two ions. Make them equals. So,
Why did you do that?
I just separated them out because once you dissolve ammonium bicarbonate in water, that's how they move first. So just to make sure that we've got all aqueous components, if we want to go through further, solve this thing for K, that's what we need. So, that's what it's going to look like on treatment. Now, I'm going to realize that I make calcium carbonate. What else am I going to make here? Ammonia. Why do you say ammonia?
Because the nitrogen is equals to the OH minus the degree of water.
I'll take that. And then our final product, as you said, is going to be liquid water. Once again, not a particularly difficult analysis. But you're going to want to remember the chemistry that's going to occur on dissolution here, giving us hydroxide ion, two equivalents of it at that. Bicarb can give one proton to one hydroxide to make our carbonate ion. Ammonia is going to give its proton to the other hydroxide ion to give us product ammonia and product water. Do we have to balance it? Well, you can, but in this case, we're just interested in what the products are.
It was for a question on the exam that we would have.
Yeah, if this were a question on the exam, you'd want to balance that. Because he might go further and ask you guys, what's K for this? In that case, you have to know all the initial coefficients. In this case, it should be pretty easy. As a matter of fact, it is. So there's that. All right. So, moving right along, the equilibrium, calcium carbonate plus water, dissolving to give us calcium plus bicarb plus hydroxide is treated with 1 molar ammonium sulfate. So we'll first write what we originally had, or that has down in the book. Calcium carbonate plus water. In equilibrium with bicarb, hydroxide, and calcium ion. All equals. Now, what we're going to do is we're going to have 1 molar ammonium sulfate. So let's start writing some chemistry. Now, what do we think a likely product of this reaction is? I think I heard it. What was that? Calcium sulfate, absolutely. So I'll start with that. Okay, so I know that if I dissolve calcium carbonate, not only does that kick off calcium ion, but what else do I get there? Its anionic component, carbonate ion. I know carbonate ion is appreciably basic and will react with ammonium to give me ammonia and bicarb. So the best way to do these, again, stepwise. Figure out where your likely products are. Figure out what you have left over. Those are going to react. Sometimes things spectate, sometimes they don't, depending on the extent of the reaction, which you can talk about by using your acid-base table. So, that's part C. Any questions on what we just did there? Okay. Next question. The equilibrium established by saturating 1 molar ammonium nitrate with silver oxide. Now, we just looked at a system similar to this before. Silver oxide in the presence of an ammonia containing species. Now, in this case, we have to pay very special attention to stoichiometry. This is a time where balance is important, so we're going to go through and we're going to take our time to do that. So, likely product, silver ammonia complex ion, right?
Why are we on nitrate?
Nitrate is a spectator ion, conjugate base of a strong acid. Now, first thing I'm going to do, I'll go ahead, I'll balance nitrogen. And I'm going to need 2 of those. Now I'm going to realize that I sort of get stopped up here when I say, okay, I'll balance silver next. Well, this is never going to work. Because stoichiometrically, I'll never have enough ammonium ion to produce 2 moles of this per mole of this. So, what we also have to include is an equivalent of aqueous silver ion. Additionally, for mass balance purposes, all liquid water. Now that's the way this equilibrium works. Otherwise, the stoichiometry of this reaction would never ever happen. We can't write a reaction, or if we're unable to balance a reaction, it's not going to occur. Now we kind of skip steps on the first couple, but in this case it comes in very, very important. The first 2 are pretty easy to balance. This one would be unbalanceable without including that silver plus ion. So, we can solve this problem for this equilibrium here. If we wanted to, but it would come out pretty simply. So we're not going to. But we will compare this to a system, question E. Equilibrium established by saturating 1 molar ammonium ammonia buffer with silver oxide. Also, without calculation, tell why silver oxide is much more soluble in this system than in part D. All right. I realize I'm going to have some of the same chemistry going on. But I've got another reagent available to me in high concentration. So I'll start off with my silver oxide, and I'll add to it the same 2 moles of ammonium ion. Realize that I'll have a similar product. Now in this case, I'm going to have ammonia in high concentration ready to react with any silver ion I might have left over. Balancing this problem becomes much easier. Okay.
So should we always add water as a product?
It's good to include to make sure that everything mass balances out correctly. Again, water, when you have solvent water, is never included in K, it's pure liquid. So in this case, I'm just including it for completeness, to show that these two are very, very similar, except for, in the case on the left-hand side of the board, you have moles of ammonia ready and waiting to react.
I was looking at charge balance, and would the minus charges come from Ag2O when it splits up? Is that why the charge balance should be equal on both sides?
Charge balance should always be equal on both sides.
Right. Well, but I'm trying to account for the negative charges, because I see you have 2 positive charges on the, well, in this case, 1 positive, 12
Okay.
positive charges.
I see where you're going.
Right.
So if you wanted to separate this reaction out and write it as several individual steps,
Okay.
all those steps would be charge balance. If I wanted to first write, for example, silver oxide is going to dissolve.
Right.
Then the first thing that I would write is going to look like this. Just draw one there.
It's going to go to the opposite. Yeah. Okay.
Now, that's going to be charge balance. Every step, if I want to write this thing in as many little steps as I want to, every step is going to be charge balance as well. So I see charge neutrality here, as well as on the left-hand side.
Perfect.
So I'm not really sure if that answers the
Yeah,
question.
definitely.
But yeah, charge neutrality, or, well, I guess charge balance is always going to be maintained
Appreciate
from
it.
antithesis products, no matter what. Very similar to mass balance. So, does anyone have any questions? Writing reactions, you're given a couple of reactants, you want to figure out products. Pay attention to stoichiometry. Close attention to stoichiometry. Really realize that something like silver plus is actually a viable product. It's what I get when I dissolve silver oxide. It's what I get when I dissolve silver chloride. But in a case like this, I'm going to realize that silver oxide is going to be slightly less soluble because I got this silver plus term floating around in my equilibrium. Whereas in this case, I have another double attack. I have acid attacking oxide on it. I've got H3N ready to react with any silver ion that might just be floating around afterwards. And in a case like this, the stoichiometry dictates that I will have some silver ion left over. So this K is going to be way, way bigger than this one. And that's what Horvath asks of us. Okay. Any more questions on that? All right, so part F, treatment of the equilibrium for E with excess 1 molar H2S. Note that silver sulfide is far more stable than any of the silver-containing components of this equilibrium. So, what is going to happen? So I have my major product here, silver, ammonium. I know, silver sulfide, Ag2S. It's going to be very, very stable. So this reaction is probably going to be driven in that direction. Now, first thing I'm going to realize, going to need two of those, balance my silver for starters. Now, what other kind of chemistry am I going to have here, other than KF and KSP for our complex ion on the left and our semi-solute salt on the right? Yeah.
You have ammonia and ammonium ion.
I have ammonia and ammonium ion, Bronson-Lowry chemistry. Now, being able to write reactions like this is really the first step in being able to accurately get at a K value, allowing you to quantify concentrations of aqueous reactants in a system like this. If you're unable to do this, you're missing the first step, and you're never going to be able to get towards the K. So if you have any problems, talk to me, talk to one of your TAs. Definitely get at it before next Friday, because you'll probably have to do some stuff like this on the exam. So, for tomorrow, flip through the beginning of chapter 20. That's where your TAs are going to get started during discussion. That's all for today. Thank you, guys.
We don't have lab next week, I know. I just like, I don't have it. That's